Hello, everybody. Welcome back. Welcome to Lesson 7 in Unit 3. Today's lesson is called Intermolecular Forces, or for short, IMF. So, in the last video, we talked about molecular polarity and how we use the bend and the snap rule. And today, we're going to cover intermolecular forces. So, here's a list of a few of them. They all pretty much work the same way. So, here's a great picture that kind of shows this. So it's using kind of a sewing analogy. So you have hydrogen and chlorine, like those different fabric pieces. Now, hydrogen and chlorine are being sewed together to form a bigger piece of, let's say, clothing or a compound. Now, the different compounds of HCl are then being held together by Velcro. And if you just pull everything apart, you get those separate pieces. So with that, these Velcro pieces, those are the intermolecular attractions or intermolecular forces, whereas the stitching in between the H and the Cl are the intramolecular attractions. So what do you think the difference is between intra and inter? So inter is where we're headed today. And inter means between different things. So if you're thinking about the interstate parkway or highway or whatever that goes through different states. If you think of intra, that is within. So intra is within the molecule. So intramolecular forces are really just like the covalent bonds. Inter means between. So the forces between different molecules. So between different molecules, within different molecules. And so intramolecular forces, again, are the forces in between different molecules. It's how different molecules behave around different people. So if you think about, Mean Girls, the movie, different people, depending on who they are, act differently with different people. And so just like compounds, depending on who they're with, they act and behave differently. They have different intermolecular forces. So again, forces in between different, and the key word here is different molecules. And so you might have a little positive dude and another positive dude may run away oppositely. That's the intermolecular force. If you have a negative dude and you have a positive dude, they may come close together. That's intermolecular forces. So the first one is ion-ion interactions. And so this is in between two different oppositely charged ions. So here is essentially your ionic bond. Again, these are very, very strong and they have high melting and boiling points because of this very high and very strong attraction. So this is essentially your ionic bond. Next, we have dipole-dipole interactions. And this is between one dipole and another one. So the partially negative side of one dipole will attract itself near the partially positive side of a different dipole. So this attraction, if I change colors here, that is that dipole-dipole interaction. So the negative kind of attracts the positive. And so this is one of the strongest intermolecular forces. As we go through this, though, you'll see that it's positive attracts negative. And that's just pretty much it. So here we have ion-dipole bonding, or really just attraction. You have an ion, you have a dipole, they come together. So you have a negative ion, will attract the partially positive side of a polar molecule, or you get that positive cation attracting to the partially negative side of the polar molecule. So if you see Na and Cl, chlorine is negative, but all the water molecules arrange themselves so the positive H is near it. And then in the other one, you have that positive sodium, and all the negative oxygens in the water molecules arrange themselves to be near it. So it's really just positive wanting to be near negative. Okay, so hydrogen bonding, this is one of the most important ones. So this is a special dipole-dipole interaction that occurs between the H of one molecule and the F, O, or N of another. So you have the H in a water molecule, and that attraction to the O in a different water molecule, that right there is a hydrogen bond. So that attraction. Now it's super, super, super important to realize hydrogen bond is not an actual bond. It has the term bond in the name of it, but it is not a bond. Whoever came up with the name was like, oh, let's call it a bond. And the world said, okay. They didn't say, wait, that doesn't make any sense. They just accepted it as is. So at this point, we're going to have to kind of accept it as is. Hydrogen bond is not an actual bond. There will be questions that will try to trick you. H bond, not an actual bond. It's the attraction between the H of one and the F, O, or N of another molecule. So I like to say hydrogen bonds are FON, fun. So again, they occur between the H of one and the F, O, or N of a different one. Now, come on. So hydrogen bonding is relatively really, really strong in terms of intermolecular forces. And things with hydrogen bonds have unusually high melting and boiling points. So if you were to compare the boiling point of water to a different small covalently bonded molecule, you'll notice that water does have a higher boiling point because of these hydrogen bonds. And you have these high boiling and melting points because it takes a considerable amount of energy to kind of break those hydrogen bonds or to break those attractions. Remember, they are attractions, not bonds. So if you look at this GIF over here, all these little white things, those are your hydrogen bonds. So the attraction of the partially positive H to the partially negative O. Now, hydrogen bonding has so many real world applications. If you think of these little water glider bugs, they're able to stay on top of the water because of hydrogen bonding. If you have ever tried to put water on a penny and see how many drops you can get, it stays together because of hydrogen bonding. If you think about your DNA, you don't exist without hydrogen bonding. And what I mean here is here are some of your base pairs. So remember, DNA is, double-stranded. We have H of one and O on another molecule. And so this attraction that keeps your two strands together is that hydrogen bond, that intermolecular force. So here's the H and the N. Remember, hydrogen bonding is F, O, N, fun. So it's H of one and F, O, or N of another. So you have the O and the H and the N, the H and the O. So hydrogen bonding is what holds your DNA together. And again, if we go back to this GIF of all the water molecules, that attraction is super strong in terms of intermolecular forces. So that's a very strong attraction. Okay. So last one is London dispersion forces. And these are very temporary and very weak. And really, it's just a temporary, induced dipole in the atom. So if we look at an example of chlorine, if we think about it, chlorine, remember, has all those electrons around it. Now, remember, electrons are always moving. They're not stationary. So for a split second, the left chlorine may have all of the electrons around it. And for that split second, that side is more negative than the other one. And so in a different example, in a different chlorine example, what if this one has all the negatives around it, and so does this one? And so for that split second, this one becomes partially negative, this one becomes partially positive, and they get attracted. Again, this is very, very temporary. Electrons are always moving, so it attracts, it goes back to normal. So we don't really talk about these, but they exist, and they're very, very weak. Okay, so just want to throw this slide in here. It belongs, but not in any specific place, so we'll just throw it in here. You might see the term network solid, and those are atoms that are all covalently bonded together, but depending on the arrangement, they form different things. So, diamond is just carbon. Graphite in your pencil, just carbon, but depending on how much pressure was applied and how the carbon atoms are arranged, that tells you, which one it is. So, random piece of info to be thrown in. So here is a good summary chart of some of them. So again, it goes over dipole-dipole, so it occurs between polar molecules. It's one of the strongest ones. Then hydrogen bonding, remember H of one molecule, the F, O, or N of another, just as strong as dipole-dipole. And then those London dispersion forces, they're temporary or reduced, and they're very, very weak. And so with this, we can kind of look at the physical properties that get affected by this. So the stronger the attractions, the closer the molecules come to each other. So that kind of makes sense. If you have a strong attraction to something, you want to be really close to it. So if you're really close and you have this strong attraction, that means it takes a lot of energy to kind of break them apart. And so that's why you have high boiling and melting points. If you think about it, if you're, really attracted to your friend, like your best friend, you want to spend a lot of time with them. And if someone tries to pull the two of you apart, you might be like, no, I don't want to go. And it takes a lot of energy to do that. But if you're just sitting next with some random stranger on a bus, and then someone's like, oh, hey, can you move? You're like, okay, cool, I don't care. So stronger the attractions, higher the energy to remove, to kind of break them apart. So higher boiling and melting point. And so, here is your lovely final summary chart. Again, goes into the compounds that are involved, the IMF that is present, and the relative order of boiling and melting point. So that is pretty much it. And it really just boils down to positive wants to be near negative. The only real main takeaway of this is the hydrogen bonding, and it's FON, fun. And that's pretty much it. That's really where all of the questions will come from with this. So as long as you remember positive sticks next to negative, you will be fine. So this is the last lesson video of this unit. Just stay tuned for a review video that will come. That is it. Next unit, we will start talking about moles, and I'll leave you thinking about what that may be. So on that note, have a wonderful day,